A hypothesis is a testable mathematical proposition. It serves as the required bridge between abstract thought and empirical verification. Researchers arrive from two directions. Deductive reasoning narrows an established theory into a specific hypothesis. Inductive reasoning takes a single observation, building toward a broader theory. Regardless of origin, the hypothesis must satisfy one condition. It must be strictly measurable against physical data. Without this operational constraint, an idea remains within the realm of philosophy. The hypothesis forces abstraction into a measurable reality. In modern methodology, researchers do not test a single idea. Instead, they pit two mutually exclusive mathematical assumptions against one another. The baseline is the null hypothesis, or H0. It operates under the assumption that any observed phenomenon is the result of pure stochastic chance. Opposing this is the alternative hypothesis, or HA. This is the assertion that a definitive, statistically significant relationship actually exists. The methodology dictates a counterintuitive requirement. A researcher must actively attempt to disprove the null assumption first. They must systematically erode the mathematical probability of random chance before they can justify validating the alternative. This binary engine prevents a researcher from confirming their own cognitive biases. Causality can only be claimed once random noise has been defeated. Consider a toy model. A child eats ice cream and subsequently develops a fever. The independent variable in this scenario is the consumption of the ice cream. The dependent variable is the core body temperature the researcher is attempting to measure. The explicit null statement for this model dictates that eating ice cream has zero mathematical link to the rising temperature. The alternative statement asserts a definitive vector of causality between the two variables. Reality introduces confounding variables. Seasonal weather shifts or an unseen mosquito bite could trigger the fever entirely independent of the ice cream. Qualitative observation cannot separate these factors. Isolating the cause requires mapping these variables onto a rigid statistical framework. This is a normal probability distribution curve. It is the statistical map used to test reality against assumption. At the center apex of this distribution sits the population mean. For our model, this is the baseline human body temperature of 98.6 degrees. Normal temperature fluctuations naturally cluster around this central baseline axis. These cluster deviations are defined mathematically as standard variance, or standard error. This mathematical variance accounts for confounding variables. It is the expected background noise of the model. This high-density central zone is the geographic realm of the null hypothesis. As long as new sample data lands within this shaded zone, the observed change is considered stochastic noise. If a sample mean remains close to the population mean, the baseline assumption of random chance remains undefeated. Now, introduce an extreme reading, the 100-degree fever following the ice cream consumption. This data point forces the reading out of the central cluster and into the extreme tail of the distribution. This horizontal arrow represents the mathematical distance between the baseline mean and this isolated sample. The central tension of the research rests on how we interpret this gap. The first interpretation argues the gap is a severe anomaly, a massive standard error that still belongs to the null. The second interpretation argues the gap is extreme enough to represent an entirely new causal relationship belonging to the alternative. Statistical parameters like t-tests and f-tests exist specifically to measure this horizontal distance. When that distance crosses a predetermined significance threshold, the null hypothesis is mathematically rejected. The rejection of the null instantaneously validates the alternative hypothesis. Scientific significance is a literal, measured geographic distance away from random chance. This precise mapping mechanism scales to manage massive, multivariable research. The ice cream case is a simple hypothesis, restricted to exactly one independent and one dependent variable. A complex hypothesis expands this model, processing multiple interconnected variables simultaneously. Applying this to our model, we might layer in cold weather as an additional input and school absenteeism as an additional output. The scope of the data can be further refined, beginning with the requirements of a universal hypothesis. A universal claim must hold mathematically true across all subjects at all times, without exception. An existential hypothesis only requires the alternative relationship to be proven in at least one localized case to be considered valid. Defining this taxonomy is mandatory. A scientific researcher cannot select a statistical test until these parameters are mathematically locked. This process converts real-world observations into rigorous statistical parameters. Pitting the null against the alternative filters out chaotic noise. This standard of proof moves from observation to theory, defeating the assumption of randomness.